All right, welcome to the Explainer. Today, we're literally turning your screen into a live laboratory. Our goal here is actually pretty simple, but it's incredibly powerful. We're going to completely demystify how scientific experiments are built, measured, and ultimately proven. We'll kick things off with real-world actions, break them down into measurable parts, and then learn the universal language scientists use to prove them true. Let's get right into it. So, to kick things off, I really want you to mentally step right into our lab with us. Imagine you're holding just a simple, everyday object, a rubber band slingshot. If you pull that rubber band back, what exact physical forces are you unleashing? I mean, think about it. Every single physical action you take creates a measurable reaction. And really understanding that dynamic, that is the absolute beating heart of scientific discovery.
Okay, let's dive into this. Picture a classic experiment setup. You've got a rubber band stretched between your fingers, basically acting as a slingshot, and you're ready to launch a little paper bullet. The whole core of this experiment is looking at the direct relationship between two shifting things, right? First, the stretch of the band, like say you pull it back 4 centimeters versus 8 centimeters, and second, exactly how far that paper bullet flies across the room as a result. And that actually brings us to our very first foundational concept here, the variable. A variable is simply any physical quantity or, a factor in an experiment that can change. It acts either as a cause or an effect. In our slingshot lab, both the amount of stretch we apply to the rubber band and the distance the paper flies, well, those are our variables. They're the physical quantities that are actively shifting during our test. Now, to do this right, every scientist goes through a sort of mental checklist. When we're identifying the parts of an experiment, we can't just randomly change things and hope for the best. That's not science. We actually have to categorize our variables into 3 specific types to carefully manage them. We have to clearly identify what changes, what's being measured, and, this is crucial, what is kept exactly the same. Let's define the first of those 3, the independent variable. This is the specific factor, the root cause really, that the experimenter freely changes and controls. So going back to our mental lab, when you intentionally decide to stretch the slingshot to exactly 6 centimeters instead of 4, that stretch is your independent variable. You are completely 100% in charge of it. Next up, we have the dependent variable. Simply put, this is the resulting effect that gets measured, and crucially, it relies entirely on the independent variable. When you let go of that rubber band, the ultimate result, so the total distance the paper bullet travels, that's your dependent variable. You didn't directly control the distance with your hands, right? You controlled the stretch. The flight distance depended completely on that action. Finally, we have the controlled variable. This represents literally all the other factors that have to be kept exactly the same so they don't mess with the final results. Think about it. If you suddenly change the thickness of the rubber band halfway through the experiment, or, a strong fan starts blowing wind across the room, how would you know if the extra stretch caused the bullet to fly further or if it was just the wind? You wouldn't. To guarantee a fair, valid test, all those other environmental factors have to stay identical. So, the really crucial takeaway here is if you want to build a valid experiment, you have to rigorously follow these golden rules. Every valid experiment has only one independent variable, one specific thing you choose to change. It has only one dependent variable, one specific thing you measure as the final result. And absolutely every single other chosen factor in the room must be a controlled variable. This strict structure, it's basically your ultimate mental toolkit for any scientific inquiry. Measuring the universe. Units. Now that we've nailed down what changes in our experiments, we need to transition to how we actually measure those changes. We're moving from the physical setup of the lab straight into the mathematical language of the lab. Now, what's really interesting about this slide is that these 7 physical quantities and their units actually make up the fundamental alphabet of the entire physical universe. We've got length measured in meters, mass in kilograms, time in seconds, temperature in Kelvin, luminous intensity in candelas, electric current in amperes, and the amount of substance in moles. Almost every single measurement you will ever take traces back to these core 7. Crazy, right? Let's define exactly what makes them so special. A fundamental unit is basically an independent measurement unit that doesn't rely on any other unit. They have their own completely standalone existence in the scientific world. And even better, we can measure them directly using basic, simple instruments. Like you grab a measuring tape for length or you click a stopwatch for time. It's direct and it's absolute. To truly grasp their importance, we kind of have to contrast them with the rest of the scientific world. On one side, we have our fundamental units, standalone, measured directly, and strictly limited to just those 7 we just saw. But on the flip side, we have derived units. These are built entirely from combinations of the fundamental units. They have to be mathematically calculated, and because of that, there are literally infinite possibilities for creating them to measure, well, anything we want.
Building blocks, derived units. Think of it this way. If fundamental units are the individual letters of the scientific alphabet, derived units are the words and sentences we mathematically form to describe more complex physical realities in our world. By definition, a derived unit is created by mathematically multiplying or dividing 2 or more fundamental units. We use these when we need to measure complex things that we simply can't capture by just, slapping a basic ruler against something or clicking a stopwatch. We actually have to use math to build the measurement itself. Let's look at how this calculation works in practice. Take something simple, like area. Area isn't a fundamental unit, right? It's perfectly built from multiplying length times width, so meters times meters, which gives us the derived unit of square meters. Or take force, which is measured in newtons. According to the formula force equals mass times acceleration, we combine the fundamental unit for mass, kilograms, with the derived unit for acceleration, meters per second squared. The final result is a highly complex derived unit, kilogram meter per second squared. And that specific combination is exactly what a newton is. And this brilliantly illustrates the sheer architecture of derived units. Just look at how this matrix builds upon itself. It's like a giant puzzle. Velocity isn't just speed, it's displacement over time, so it's derived by dividing meters by seconds. Density requires dividing mass by volume, giving us kilograms per cubic meter. We are literally stacking our fundamental units on top of each other, using multiplication and division to perfectly describe exactly how the physical world behaves. Proving the math, dimensional consistency. All right, we are now entering the final and honestly the most powerful stage of our mental lab session. We know our variables, we know our units, but how do we definitively know if our scientific formulas are actually true? Well, we use a rigorous process called dimensional consistency. Here is the absolute ultimate rule you need to know. An equation is only mathematically valid if both sides share the exact same fundamental units. You simply cannot equate apples to oranges in science. If the left side of the equal sign breaks down to a specific combination of fundamental units, the right side must break down to that exact same combination. Let's move to our next example and see how this builds a flawless scientific proof. We want to validate the equation force equals pressure times area. Okay, step 1. We take the left side, force. As we just learned, its units are kilograms times meters over seconds squared. Now, step 2. We break down the right side. Pressure is defined as kilograms divided by meters times seconds squared, and area is square meters. Step 3. We combine that right side by multiplying them. The math cancels out one of the meters, leaving us with kilograms times meters over seconds squared. And step 4. Both sides perfectly match. The fundamental units are identical, which means this equation is absolutely mathematically valid. But hey, what happens if someone comes along and makes a completely false claim? What if they boldly state that force equals pressure divided by area? Let's run it through our unit analysis, which honestly acts like a universal lie detector for physics. The left side is still our standard force, kilograms times meters over seconds squared. But on the right side, when we mathematically divide pressure by area, we get kilograms divided by meters cubed times seconds squared. Now look at step 4. The units completely clash. They absolutely do not match. Therefore, we have scientifically proven that the equation is totally invalid. And just like that, our lab session comes to a close. By truly understanding the distinct roles of independent, dependent, and controlled variables, and by mastering that alphabet of fundamental and derived units, you've unlocked the true mechanics of scientific inquiry. You now know exactly how to structure an experiment and, more importantly, how to mathematically prove the results. So I'm going to leave you with this final, provocative thought. Are you ready to step out of this explainer and analyze the variables and units in the world around you? Because I promise you, every single action, every force, and every movement in your daily life is just waiting to be measured.